Welcome to the series seminar today. We're very glad to have Zheng give a talk today. He's a MIT fifth year PhD student at MIT working with David. Previously, he got his bachelor from McGill University in computer science and biology with a minor in mathematics. And he's broadly interested in the theory and application of machine learning. And today he'll tell us about robustness of image classifiers.
All right, hello. Thank you for that introduction. So, yes, I'm here to talk about the fundamental limits on the robustness of image classifiers. Here, I do have a QR to a website which has a link to the paper, the full paper, and as well as a few minor demos and a video that sort of overviews this project. So, the outline of this talk will be, first I'll give a brief introduction to the problem, some motivations, and maybe define what robustness is in this context of image classification. And then, and also state what the results are. And then I'll actually go into some of the proofs. I'll talk about the three theorems that we have. So our theorems, there's three of them. Basically, the first one is an upper bound on what the robustness that you can achieve in image classification. Theorem 2 is a lower bound on, which is basically you can construct a classifier that is robust, that is at least this robust. And the third theorem is something slightly different. It's about how the robustness that you can achieve has a dependence on the bit depth of the image space that you're working in. And finally, I will conclude with some finishing thoughts. All right, and with that, let's get started. So, part one, introduction. Image classification, right? I'm sure everyone is aware of this. This is the task of partitioning the universe of images. Write an algorithm that ingests an image and outputs the label of the class that it belongs to. For example, you get a picture of a rabbit, you output the label rabbit. You get a tree, you output the label tree. You get a hat, you output a label. And this is sort of this. I would say this is sort of a problem that was extensively studied in the mid to late 2010s, right? And in the year 2023, this is, in essence, a solved problem, right, with the progress in deep learning. Or, I would say that, but there are certain issues with the current classifiers that we have. Namely, the image classes that our current classifiers tend to be brittle. So this is a classic illustration, right? So instead of, making my own, I just drew a little cartoon over here. We can take an image that ostensibly looks like, ostensibly belongs to some class. So here it's a rabbit. We can apply some kind of imperceptible perturbation, and that will cause the deep learning model to classify as something completely ridiculous, like, for instance, a tree. Again, this is a cartoon, so this is not actually going to work, but this is a sort of well-known phenomenon at this point. And this phenomenon is prevalent across various image classifiers. Like, we construct a whole bunch of different image classifiers with different architectures using different methods, and they all seem to have this problem, even ones that explicitly try to avoid this problem. So this kind of leads us to a question, that being, is it possible to construct a robust classifier? Robust in the sense that, it doesn't have brittle image classes, that it doesn't have this problem, that you can't apply imperceptible perturbations to images and cause them to completely misclassify. Is it possible to construct such a classifier, or is there some fundamental quality to the universe of images that sort of forces something like this to happen at a very basic level? So, there has been some literature that shows that, you can use certain techniques to sort of make these image classes less brittle. However, there's also a line of work that shows that there are some fundamental limits, and these limits are classifier agnostic, which means it doesn't matter how you build the classifier, it's just a quality of the image space. It's just a quality of the universe of images. And here I'd like to highlight some of the discoveries in the past, prior work. All right, so in 2018, there was this work that showed that image distributions that are spawned from generative models have a robustness that is bounded by the Lipschitz constant. So you can always perturb an image so that it misclassifies with a perturbation that is of size that is bounded by the Lipschitz constants of the generative model that generates that image distribution. And the techniques they use is they use a Gaussian isoperimetric theorem, and they use some Lipschitz continuity arguments to prove this. Then there was also this other work that showed that if you have some probability of error on your classifier, right, you can get your error rate to be very low, but you always assume that there's some error that happens because this is a learning task. What they showed was assuming a finite error probability, so non-vanishing, then you can modify root n of the inputs. So your input is a bit vector, right? You input a bunch of bits, and you can modify root n of those bits to force the classifier to misclassify. And then later on, this result was generalized slightly to a different distribution of inputs, a different problem space.
Sorry, and the number of bits here, or like root n perturbations?
Yeah. So n is the number of bits in this case. Yeah. So, any other questions before I move on to what our results are about sort of what the definition of robustness is in this context, what we're trying to do here.
So when you say that the classifiers are susceptible to perturbations, does this mean that it can change to a different image classification?
Sorry, it can change to a different image classification?
Like, what do you define by being susceptible to a perturbation?
Right. So their image class, so the classifier induces classes in a way such that, the images in that class can be moved outside that, can be manipulated to be outside that class with a small perturbation. Does that make sense?
Those are called adversarial inputs.
Oh, yes. So, thank you, yes. Traditionally, this literature is known as the adversarial robustness literature as well.
Was that Harper's isoperimetric theorem? Is that Harry Harper? L.H. Harper?
Yes. Oh, yeah, I should also mention the techniques for these two papers, right? So Harper's isoperimetric theorem on the Boolean hypercube, and here is some concentration inequalities. And part of the reason I list these out is because these are all the techniques we'll sort of leverage in our results as well.
When you say square root n perturbations, is the objective during those perturbations to get the same type of image like that, the rabbit, then you apply the perturbation on root n bits, still get rabbit, or is it kind of like just that's one thing, a noisy image that
Yeah, you get a different class. That's sort of the idea. So, okay, I'm leaving out a little bit here. There's some subtle differences to these different works. What they're claiming is there is an error region. With finite probability, the classifier misclassifies. It says with root n perturbations, you can move an image into that error region. All right, okay. So forget everything I just said because we're going to sort of redefine everything in our space. Okay, so our results, right? Let's go. So theorem 1 is a theorem on the non-robustness of the universe of images. So given a universe of n by n images, so n pixels, if you have some class S within that universe that consists of at most half of that universe, then to change the class membership of most images within that class, so for most images in S, you can change its class membership with either you can just modify O of n pixels in that image, again, n being the side length, or apply a perturbation with a p norm that is on the order of n to the 1 over p. So that's theorem 1. It's the non-robustness results.
Sorry, how is this different from the root n result you just said? Is it now because it's most of the images?
Ah, right. There's so this is different from the root n results because a pixel can be encoded with more than 1 bit, right? So,
Okay. I shouldn't be thinking of like single bit pixels.
Yeah. Although like a lot of the discussion will surround that, but like it's a stronger result in that sense. Okay. Let me move on to theorem 2, which is talking about the optimality of theorem 1, which technically, right, it says the same thing given your universe, right? You can construct a class S such that, with small o of n pixels, so here big O, here small o, you cannot change the class of most images in that class. So most images are actually robust to small o of n pixels, or a p norm of size smaller than n to the 1 over p. And the third one is about the bit depth dependence. Again, it's the same thing as theorem 1, except here you see there's a bit depth dependence. So you have the robustness and you have it divided by 2 to the bit depth. And I think it's best to talk about that when we actually get to that in our proof, since this is sort of separate from the other 2 theorems. I'm just mentioning it here to sort of prepare everyone for what might be coming up. All right, so that's the introduction. We're going to move on to the proofs now. Okay. All right, again, theorem 1. For all but a small fraction of images in a given class, we can change their class memberships by changing only O of root n pixels. So I'm switching the definition of n. I apologize for this. But so n, and then now we're saying n is the total number of pixels in the image, right? So what used to be n squared is now n. And for the rest of this talk, I will not change this anymore. This will be fixed from here on out. So, okay, an image consists of n pixels. You only need to change root n of the pixels, where n is the number of pixels in the image. So to start with, images are just grids of pixels, right? So here's your universe of all images. What an image looks like in there, here's a 4x4 image. We say 4 is root n now. And we just fill in the pixels with different colors. So, and colors can be indicated by numbers. So here's 0, right? And the darker regions are 1, and the sort of grayish regions we'll say is a half, right? And this we could give like the label A, for instance, right? Straightforward. And sometimes it's useful to think of, these, to sort of flatten this, right? And instead of thinking of this as just an image, just think of them as vectors. This will make like the idea of distance and everything much more obvious. The other thing worth mentioning is that the pixel values in our setting are taken from a finite set of evenly spaced values between 0 and 1. So for example, 0, half, 1, or like 0, 1/4, half, 3/4, and 1. All right, so that's how we define an image. Next, we're going to use these images to build a Hamming graph. And this is, so again, Hamming distance, right? Hamming distance just sort of counts the number of mismatches between 2 vectors. So here, right, 2 mismatches. It doesn't matter if, how distant the 2 are. It's a mismatch is either a mismatch or not a mismatch. And so the only way to get rid of this mismatch is to make them match exactly. And a Hamming graph is you take these vectors and you just you take the universe of all vectors of a given size, and where each entry comes from the same alphabet, and you link together any pair whose Hamming distance is 1, is exactly 1. So if the values in your vectors are Boolean valued, right? If you have bit vectors, then you just get hypercubes. So here you have 3 entries, so actually you just get the cube. And here's just a visual of the Hamming graph on this universe of 2x2 binary images. And one of the nice things about the Hamming graph is the graph distance is actually coincides exactly with sort of how many pixels you're modifying, right? So if you're traveling 2 edges, you're modifying 2 pixels within that image. Any questions so far? All right. So not all Hamming graphs are hypercubes, right? So when the alphabet is not binary, you don't get a cube. Here you have 3 possible values that pixel values can take, and you get this messy-looking Hamming graph. Okay, so the next concept I need to talk about is vertex expansion. Vertex expansion is basically if you take a graph, right, you can take, and given a set within that graph, you can consider this delta S here, the nodes colored in red, as sort of the surface of that set, the boundary of that set. You can sort of think of this as an expansion operator. So if you expand S, you take the boundary elements and you add it to the sets. You can think of that as a bit of an operator. And the vertex expansion number, the isoperimetry number, is the minimum boundary that you can get out of, you're trying to minimize the surface area with respect to volume, in a sense, right? And the constraint here is that the sets that are under consideration has to be smaller than half the universe, because, the complements would just be the complements, right? You would just get very small things when you start taking, like, most of the vertices. So that's why this constraint is here. This is one way of defining vertex expansion. So having defined vertex expansion, I'll state the theorem, which, for a Hamming graph, the vertex expansion on a Hamming graph generated from q to the n, so take some alphabets, right? Take its n-fold Cartesian product, you get a universe of vectors. And then you build a Hamming graph on that. The vertex expansion on that Hamming graph is on the order of 1 over root n. So basically the ratio, so for any set, right, if you expand it, you will increase the size of that set by, 1 over root n, a factor of 1 plus 1 over root n. That is the vertex expansion property on Hamming graphs. Are there any questions? All right, good. So how do you prove this? There's sort of 3 ingredients here, which I'm not going to get too deep into. But first, you have Harper's isoperimetric theorem on Hamming graphs, which is a statement on, which says that, sort of it basically says, like, on Hamming graphs, this is sort of like the smallest boundary that you could get. It sort of looks like this. The second part that you need is that you need the monotonicity of the quote-unquote binomial frontier, which just says that the ratio of this to this is larger than the ratio of this to this. As you move towards the center, you're just going to get larger and larger. And the third is you use a concentration inequality to, once you manage to push, like, this result to the boundary, you sort of just take a concentration inequality to find that, oh yeah, it's 1 over root n.
Sorry, what's the randomness with which, or like with respect to which you're applying the concentration inequality?
The concentration inequality, let's see. So it's not really randomness per se, but like, because things sort of look like a hypercube, right? You can sort of think of it as a binomial distribution, and then you can apply the concentration inequality. Yeah. Okay. And so a neat corollary of this fact, right? The fact that, you expand, every time you apply the expansion operator, you increase the size of your set by 1 plus 1 over root n, is this neat corollary where if you sort of apply your expansion operator root n times, then you get an increase by a constant factor, right? And of course the proof is, so this is between 2 and 3, right? It's between 2 and e, but. And here's a nice little visual that shows that, right? You start with a fairly small set, and then you expand it 3 times, and you get pretty much half the entire universe. Okay, so now we're ready to actually prove the theorem about non-robustness. And this is sort of a proof by contradiction. So again, we start with our universe of images, right? We now take a subset S that, that is our class of interest. Here I've, indicated that the class of interest is like the pictures of cats, for example. And here you have pictures of things that are not cats that sort of live outside this set. And again, we're assuming that like the size of this set is smaller than half the universe. Now, suppose, or like let the subset R be the subset that is robust, by which I mean like you can't apply less than 12 root n pixel changes and change its class membership, right? So this is R. And now suppose by way of contradiction that, the size of R divided by the size of S is greater than or equal to 0.05. The number here, you can plug in different values of this. I'm going to use a specific set of values that work, but in our paper, right, there's the general form of this theorem exists. So greater than 0.05. So basically R is greater than, or rather S is smaller than 20 times R. Well, okay, so if we expand R, if we apply the graph expansion operator 12 times root n times, right, then by our construction, by our sort of assumption, this can't be larger than S, right, because we can't change its class membership with more than S things. So again, like the stuff in R, right, is things that are very, obviously something in one class can't be manipulated to be another class, while the other elements might be like more questionable as to what they are. Here, so elements in the expansion sort of look like corrupted versions of R, right? And by our construction, because we said that you can't manipulate elements of R to be, to change their class membership with this many pixel changes, then that means this expanded R must lie within S. But then if we apply our corollary from earlier, right, we'll find that after expanding this, the amount by which you've increased the size of the set makes it bigger than S. And so by definition, you have R is within, the expansion of R is within S. By the corollary, right, the size of R is smaller than the size of S, is smaller than the expansion of R. And this is a contradiction because you can't be a subset of something while being bigger than something. And so contradiction, and therefore this supposition was incorrect, and R, the size of R over the size of S must be smaller than 1 over 20.
Do you expand R by applying the perturbation?
Sorry, what?
Do you expand R by applying the perturbation?
I expand R by like applying all possible perturbations of size 1, right? So if I apply this operator 12 times root n times, then I get all possible perturbations of 12 times root n.
So each expansion just finds like adjacent things in the Hamming graph?
Mm-hmm. Exactly. All right, any more questions?
So I guess this assumption that sort of like robust fraction is a constant fraction of S, like if you really wanted to, you could do away with it, and then you'd have to expand like something like log of the size of the set of S or something. So maybe that's not a question so much as just a comment. Yeah, but I guess it's you're saying like if you want to be robust at all, just by virtue of like the Hamming graph being expanded,
Mm-hmm.
You don't have to perform that many expansions until you escape any set.
Yeah. So I guess, yeah, that would be an extension to this theorem, right? So here I'm just talking about like constants and constants, but yeah, you can make this, if this is like 1 over log n or something, right, then this would be reflected in how many times it would have to expand. So I think the log n would show up like 12 times log n times root n or something like that. All right, well, that's sort of theorem 1. There is one minor corollary to go through. So what we've just shown, right, is like all but a small fraction of images in a given class, has this property that we can change their class membership by changing O of root n pixels. I've colored like the small fraction and root n with the same color to indicate that they're related, right? This is a trade-off. The smaller you make this, the larger the constant that the O is hiding becomes. Now the corollary is, since we said pixel values are bound between 0 and 1, well, then that means like the L0 norm actually sort of upper bounds all other p norms, right? With this the 0 norm raised to this power sort of upper bounds like the p norm. So therefore we get a result on all the other p norms as well. Okay, so that's theorem 1. Moving on to theorem 2, we have an image. There exists an image class such that for all but a small fraction of images in that class, we cannot change their class memberships by changing only small o of root n pixels. And we will actually start by proving the result on the L1 norm, the Manhattan distance, and then going back to L0. So this is how we construct the class, right? We'll just construct this robust class here. So here's the class. All elements of this class, this class consists of elements whose L1 norm is smaller than n over 2, where n is the total number of pixels. And so here, right, here's our universe of images. N is 4, so n over 2 is 2, and so this would be S, right? Now, if we take more images, right, we can build this. There we go. We can build a histogram here of where the pictures land according to their L1 norm. And again, this is the classification boundary. This is an S, this is an S, and these are the things that are not in S. Now, by the triangle inequality, right, the Manhattan distance between images is at least a difference in their 1 norms, in their 1 norms. So, in other words, to travel along this, right, you need to apply a 1 norm of at least this length. So, if you have an image here and you want to move it here, you need to apply an L1 perturbation of n over 2 at the very least. And so this lets us very easily see, so now we can very easily see that these are the non-robust images, right? Non-robust to O of root n, if, that is the size of small o of root n. These are the non-robust images. And so by the central limit theorem, right, this is a bell curve where, and by the central limit theorem, any slice that is smaller than root n has measure 0. So it's a vanishingly small proportion. And which proves our theorem. This is a robust class. This is a class that is robust to L1 perturbations that are smaller than root n. And of course, so moving to L0, right, we just observe that, the L0 sort of is, like it just counts mismatches, right? And because differences are bound between 0 and 1, you're just increasing them if you move to L0. So the L0 norm also are robust. Was there a question? No? Okay. The movement to higher norms is a little more interesting. So first, let let G be the size of the gap between the evenly spaced pixel values. Remember, we're selecting pixel values from a finite set, right? So they are evenly spaced, and let G be that gap, be that space. Then we can do the following manipulation. The LP distance between U and V, is defined as this, right? You take the difference between every coordinate, you raise it to the power of P, and then you add them up, and then you raise them to the power of 1 over P. Multiply and divide by G here, and then move G all the way outside the brackets. So you just end up with this. Now, here you have this term, right? The interesting thing is this term is either 0 or it is at least 1, right? Because the smallest difference between U and V is G. It's the gap between the values. So if they're different, they differ by at least 1. So that means that this, so anything larger than 1 raised to the power of P is larger than, the same thing raised to the power of 1. And so this gives us this inequality, which then gives us this result, right? And so if you ignore if you sort of take G, this gap, and put it into the constant, right? Consider it as part of the constant in the order in the big O term, then you end up with a robustness result. It says that, you can construct this robust class as well. So that completes our proof. Before I move on, I guess I'll pause again for questions. All right, great.
Oh, yeah. Wait, so I guess getting these kinds of results, you're assuming that sort of the universe of images is given by just this Hammond graph, which assumes that you're basically allowed to arbitrarily manipulate pixels, and you can sort of always go from one image to another, and that sort of all possible images are sort of legitimate images in some sense.
Yeah.
You start I don't know, carving some things out as this is not a valid image, or maybe I don't allow myself to move from this image to another image, then you might lose this expansion property. Do you have any thoughts on I don't know, if you get rid of all the images that are not, that we would not actually treat as just not static, you still have some sort of interesting space of images, which is maybe still expanding and exhibits these properties, or
Right. So let me think. So one thing that so in one of the papers I actually mentioned, right, the first one out of the 3 that I mentioned actually has an approach that you can sort of adapt to this, where what you can do is consider a function, right, that takes as input a regular, consider a diffusion model, right? It operates on the space of uniformly distributed images and sort of moves things towards the natural distribution, which I presume is, what you're thinking of, right? Of interest, or whatever set that you're interested in. Then we can consider as the Lipschitz constants of that function, right? And so you can apply this bound multiplied by that Lipschitz constant. What you can say about that Lipschitz constant is ultimately an empirical result, though. So I don't know if there's something theoretically interesting you can do there. Does that answer the question, or?
Maybe, yeah. It wasn't a super well-formed question, but I guess.
Well, I hope it was helpful at least.
So when you say the dependence on G, what do you mean?
So this is O of n to the 1
Yeah, that's
half
what's
p.
inside, right? Because the 1 norm is square root of n.
Yeah. So there's a divided by G here, right? That's swallowed into the O.
Oh. Sure.
Yeah. Which, perfectly leads us to the next point that I'm going to make, which is that, if you ignore the G, then, we have this nice result that shows that theorem 1 is sort of optimal. However, there is a G, and a natural question you might ask is, well, is this G necessary, or is this sort of a fault with our construction? Is there a way we can prove this result that doesn't involve G? And theorem 3 says no. So again, for all but a small fraction of images of a given class, we can change their class membership with a perturbation that has a 2 norm. So again, right, the G happened when we tried to generalize to things with norms above 2. So this only happens with the 2 norm or higher, which is interesting. So with perturbation of a 2 norm of O of root n divided by 2 to the b, where b is the bit depth of the image. And just to describe what bit depth is, right? Bit depth is how many bits are used to encode the image. So in bit depth 1, you just have black and you just have white, and you can make an image. Bit depth 2, you have some grays in between here, right? So you can sort of get shades and so forth. And of course, the higher the bit depth, here is an example where you have 8 colors, right? Encoded using 3 bits. You have a very well rendered image here. All right, so how do we actually prove this? Let's see. So the proof outline is also somewhat interesting. What we're going to do is we're going to define a procedure to escape this set that's under consideration. So here I've drawn a cartoon of like what we're considering, right? We're taking these images and we're considering them in sort of Euclidean space, right? So this is like the sort of 0, 0 image, 2 pixels. This is like, you know, partially shaded, and this is dark because it's all the way here. And this is the completely dark image. And in this cartoon, there's only 16 images, right? And we've singled out these 5 to belong to the class S. And what we're going to do is we're going to define a procedure to escape S. We're going to bound the size of the escape route, right? And that sort of tells us that, you know, you have an escape route that is this short. And then our procedure will also have a probability of failure. So because, you know, if you find something that's just, because you can't bound the probability, bound the size of the escape route if you don't allow the algorithm to fail. So if we bound the probability of failure, that sort of bounds the amount of like robust images within this set. So here's the procedure. Start by selecting a random element of S. Second, perform a random jump within the cell of that image. And now, at this point, you're uniformly distributed in this red region over here. Now, the next step, once you're uniformly distributed here, find the nearest point that is outside the red region. So here's an example, right? If you started here, then you did a random jump here. At step 3, you want to find the nearest point that is not in the red region. So now you're here. And then step 4, if that point that you found is greater than a distance of 100 away, if this jump is 100, and again, 100 is just a number I'm plugging in here. If it's 100, more than 100, just fail. But if you haven't failed, then just find the nearest point that doesn't belong to us. And so this is the escape route that we found. And so if we succeeded, right, if we didn't fail, then the total distance is no more than the sum of the random jump, which is root n over 2 to the b. Step 3, which is, you know, if we succeeded, it can't be more than 100, so O of 1. And then step 5, which is finding the closest point that does not belong to S. Well, because you're on a grid, right, every point is within O of root n over 2b. And again, I should also clarify, these are all Euclidean distances at this point. And so adding all of those together, applying the triangle inequality, we find that the overall escape route that we have found is O of root n over 2 to the b, which matches what is in the theorem statements. Now we bound the probability of failure. So the condition of failure is after your initial jump, you're further than 100 units away from the boundary of this red set. So sort of this dark region over here. And we can show that this probability is smaller than 1 in 20. Again, another number that I'm just plugging in. And this is an isoperimetry result. You can use the fairly famous Gaussian isoperimetric inequality here to show this. Okay, so this probability is fairly small. And how does this help us? Well, during your procedure, right, there are 2 points in time when you're cooked. One, you might, after selecting an element from S, you might just be cooked because like the element that you selected in S might just be too far from the boundary. Or two, you might have performed a bad jump. Your random jump might have been bad. So note that if you're like, if you haven't been cooked after step 1, if it's step 2 that cooks you, then you're actually still fine. The original point that you selected is fine because that means there exists a path there that is fine. You just got unlucky. So the only bad points are the points that cook you after step 1, right? And so by the chain rule of probability, right, 1 in 20 is greater than the probability of failure, which by the chain rule, probability of cooked after step 1 times probability of cooked after step 2, which is greater than the probability of being cooked after step 1, which is the probability of bad points. And so we bounded the probability of having a bad point by 0.05. And that's it. Again, you can generalize this to higher norms. We've already done this, so. That's it. That's all the proofs. Any questions on this one? Cool. So, let me conclude then with a few thoughts. So one, you can see this as a bit of an impossibility result on whether you can build a classifier that is robust at all, right? This is bad news, but but not necessarily. There are ways that you can circumvent this, and one was brought up earlier, right? Maybe you don't care about all the images in your universe. Maybe you only care about certain images within your universe. So, maybe you only care about the all black image and the all white image. Well, in this case, you're pretty robust, right? You do a few perturbations, you're going to end up somewhere here. You do a few perturbations here, you're going to end up somewhere here. You're still going to be able to very much classify these as this and these as this. So that's one way you can circumvent the results, right? You can still build robust classifiers with respect to distributions that you might care about. The other thing to note is our result is classifier agnostic. And that means it necessarily applies to the human visual system. I've gotten a few complaints about how, the human visual system is very complex, right? There's a lot of things to consider. But there's a way to sort of factor out all that complexity, and that is with like the sort of the following procedure, right? You take a person, you put them in a room, and you don't let them have outside contact except through this monitor. And now you've built a classifier. In order to use this classifier, right, you just feed an image into it. Now the screen will pop up. It'll give you the image, and then it'll ask you to give it a label, and the person will be forced to give it a label, and that will then be returned to the person who asked the question. Right? This is a classifier, and it is based on the human visual system. So, and because this classifier fits all the descriptions of like a classifier that, our theorems are on, our results apply. Our results apply to this system, and therefore it applies to the human visual system. Which leads us to question like, okay, so these are small perturbations, right? You only need to change a number of pixels that are proportional to the side lengths of an image. So for most n by n images, right, that means, if you only need to modify O of n pixels, that's tiny compared to the total number of n squared pixels in the entire image. But that is sufficient to draw lines, right? Yes?
Yeah, is that a question regarding that? Can you arbitrarily pick those
those pixels, or do you just guarantee there's an existence?
It's just a guarantee of existence. Right. So, you know, like, you can draw things, right? And you can draw them with relatively few lines. You don't really need a lot of pixels to make these images. And so this is kind of suggestive. I don't know. I'm still thinking about this, right? Like this is, and like this doesn't solve the full problem. There's the bit depth dependent bound, which is a little too non-robust for line drawings to really account for. But at the same time, like it is interesting that we find lines very salient, and at the same time, lines are, you know, O of n pixels. I think the final point then I want to make is that the problem with classifiers isn't necessarily about robustness, right? A classifier that is non-robust is kind of fine as long as it is non-robust in the same ways that humans are. You know, I take a random shape, but with very few perturbations, I can, you know, add semantic meaning to the picture that wasn't there before. And I think that's it. So this is the list of references. I had little notes throughout the entire talk, so these are what they're referring to. And thank you. So, questions?
So for your one, it's like a statistical analysis. I was wondering, does it also have computational implications? Like, for example, if you just pick a random walk, then with certain probability, you know, find the value.
Right. The way I presented it, yeah, it's just an existence result. And I think you can show that, you know, in general, like given a picture, find me like the nearest sort of picture that is not in that class. That's NP hard, I think.
For
I can give you a classifier. I can build a classifier that is like, you know, a polynomial size. I give this to you as input, and I ask you, and then I give you another image, and then I ask you to find the nearest image to the image that I gave you that the classifier classifies as a different class. That's an NP hard problem, right? Reduction to 3-sat or something.
I don't necessarily have to find the nearest one.
Oh, right, right.
You will find one that's sufficient.
I mean, because the graphs are like vertex expanding, the mixing time will be low. So you can argue that high probability will like mix quickly over just like polynomially many steps and then be outside of the initial class as long as it's like a small, you know, not a huge fraction of like the entire space of images.
Oh yeah, that's true, yeah.
I guess if you want the nearest thing, then all of a sudden it's harder.
Right, because like the adversarial examples are bad because they're sort of imperceptible, right? Because they're near to the original example. So it shouldn't be too hard to find something that gets into a different class. But yeah, I think that's an interesting question.
If I understand correctly, you're saying that, okay, you give me a classifier and an image, and I tell you if you change this many pixels, you know, go out of this boundaries.
Mm-hmm.
And you know, from an adversarial perspective, you're just saying that, okay, you know, we are still a cat, but we change these pixels and went out of the class, but the image is still cat. But the question is, you know, what if we have two classes and we change this n pixels or whatever, and we get another meaningful thing that is, you know, a separate thing. It's out of this class, but it should be out of that class.
Yeah, and that's sort of what I was trying to allude to with the last slide as well, right? The idea that, you know, it's not necessarily a problem with robustness, because robustness, as adversarially defined, is sort of about like how thick the sort of boundary between like different classes are, right? But as you know, the line drawing example gives, right? Like, yeah, these boundaries are thin, and maybe they should be thin. And so the problem is sort of really alignment, right? It's not, you have a problem when the classifier thinks differently than a human.
I have a follow-up question, which is, yeah, I mean, I guess on this point of alignment, like, do you have any sense of what's sort of like the right formalism here? Because, you know, like, if I stick googly eyes on like whatever is in the picture, I can probably convince people that it's something else, and this is like a small perturbation, but I don't think we understand that as like delinquent visual behavior or something. And I guess, as you said, it's like seemingly the issue with these perturbations are like we can do perturbations that to people do not seem like meaningful perturbations, but the classifier do. Like, what's the, other than saying like we just wanted to do what people do you have any thoughts about sort of like what the sort of like right sense or like what we should allow in terms of perturbations?
Yeah.
Like permissible perturbations that lead to different things, I guess.
Yeah. I think it has been said that like in some sense, right, this alignment problem is basically vision complete, right? You solve the alignment problem, you solve vision, you solve basically everything. So that is sort of, I know that's sort of a trivial statement to make, but at the same time, I don't know. Yeah, like the whole idea of having this robustness definition is to get away from saying, oh yeah, you should just align with the human. And I guess like part of the contribution here is pointing out like the flaws with that, right? And there is definitely other works that point this out and so forth. As to what works, I would love to know. I would love to find out myself as well. And I think like this is something I am looking into as like a possible direction of research. Yeah, so something cognitive science related, right?
Would you drive a vehicle that uses image classification system that can be given an adversarial input and lead to injury or death?
Are you including humans in that? I guess I took an Uber here, so. No, it wasn't driverless, but like humans are also susceptible to adversarial. You change a stop sign to say go, and suddenly, add a 0 to the end of the sign, right?
No, just down south at Berkeley has had her students put 2 strips of white paper and 2 strips of black paper, change the classification from stop to 45 miles an hour.
Oh yeah. Right. I see. Yeah, I know. It is scary. I don't. I don't know. No comments.
I just wanted to hear more about your future work. What you think you can.
Oh yeah. So like my little spiel about like the line drawings and so forth is sort of where I'm thinking of like what might help align these systems, like maybe things like training them on these things, right? There has been some work on this. I've looked into it a little bit, but that's sort of what I'm thinking right now. But yeah.
Do you think that there's definitely some semantic changes, but also some sort of like localization.
Some what? Sorry.
Sort of like spatial component that whatever you apply to change actually matter.
Mm-hmm.
I don't know if you think that could be a way to like shrink a little bit the problem.
Sorry, like the spatial.
So, for instance, if you just humans
Mm-hmm.
to classify a dog, and then you tell them what they're looking at, they're pretty consistent with everything. Like there's somewhere in the beak or the eyes. That is the first thing that they look.
Oh, right.
The classification. And then if you actually messed up things there,
Mm-hmm.
for example, take longer time for the image or something, you get it wrong.
Mm-hmm.
So I guess I don't know. It seems like there's something like in the where you're applying the changes that could shrink a little bit the space.
That's true. Yeah. So that could be like an experiment you run on, like, I mean, I believe there are techniques that can like they look at the pupils, right, and see like where they're pointed, and and see like how the decisions are changing as your focus darts around the picture. So that could be that could be potentially helpful in aligning these systems. Oh, all right. Well,
Let's thank the speaker again.
thank you.